Thus, we know that for every object or rigid body, for every translation of that rigid body, for every orientation change of that rigid body, we will always represent it by a 4 by 4 matrix, and that matrix is called as the homogeneous transformation matrix. So let me define it one by one. That is, it's a matrix of any frame that defines the orientation as well as the position of the matrix. The second point is that it's a square matrix. It's a square matrix. Now, why is it a square matrix? The reason is very simple, because we have two kinds of matrix operation going on here. First is that we have to take the inverse of this transformation matrix. So in that case, we can have a square matrix whose inverse can be taken very easily. That's why we have it as a square matrix. So the first reason is easier to take inverse. Then the second reason that we have is that when we multiply two matrices, then we will get the same size matrix if both the matrices are of a square size. So the second reason will be multiplication. Multiplication will lead to same size matrix. So we will basically have a square matrix for a homogeneous transformation matrix. So it's a square matrix, so it can be either 3 by 3 or it can be a 4 by 4. Generally we will go for 4 by 4 because already we have studied that, and we have seen that the frame is generally represented by a 4 by 4 matrix in which there are 4 rows for nx, ny, nz, 0, ox, oy, oz, 0, ax, ay, az, 0, and the last is the position one, which is px, py, pz with a scaling factor of 1, and that is the homogeneous matrix. As you can see, it gives the information of orientation and position. That is the same point that we have written in the first. The main use is that for understanding what is the desired motion going to deliver us, we can multiply many transformation matrices together. So let me write that as a point. So we can say it is multiplied with other transformation matrix to get the desired orientation or translation.